So today we have the joy of having Mauro Mariani from Higher School of Economics in Moscow, and he's going to tell us about fluctuation of random homology. Thank you, Mauro.
Thank you, thank you. So thanks a lot for the opportunity to speak here. And this is a joint work with Artem Galkin, who is a first-year PhD student in our faculty. And this is a bit of a continuation of his master thesis. It should appear shortly on the archive, because if it doesn't appear shortly, he loses a good part of his fellowship. There are quite strict rules in Moscow, so certainly in the next few days, by the end of the summer, compulsion. So, okay, that's just plan of the talk. I will try to annotate the screen, and so there is a bit of geometry, but not like hard differential geometry, just simple things. I will try to, I'm not an expert in differential geometry as well, but I know that anybody in probability, including myself, forgot most of these ideas, but it's really, I mean, there is nothing non-trivial about it. Nothing trivial about it, so nothing non-trivial about it, so it should be okay. So what is the idea? I will discuss the simplest invariant possible, but like if you have some curves, say on a manifold, there are some classical invariants that are, of course, object of study of geometry since forever. And for instance, it's not about this, but it's a nice example, is the linking number. Yes, like you have some curves, two curves, like in this case, and how many times they overlap each other. Okay, in this picture, the linking number is 2. And, and of course, if you make some continuous deformation, this doesn't change, right? Unless you unlink these knots. So what is nice is that there is a differential description of this number. For instance, this in R2, okay, you just integrate. Okay, here S1, these curves are closed. So S1 is just, if you want, the parameter T of the curve, S and T of this curve. So this is gamma 1 and gamma 2, okay, are these two curves. And like the number, the linking number, how many times you need to overlap them to take these two curves away one from the other, has a nice writing due to Gauss as okay, you make the determinant of the derivative of gamma 1, derivative of gamma 2, gamma 1 minus gamma 2 divided by the distance to the cube, integrate the SDT, and you get this number. Or, of course, very classical things like the homotopy of a curve. Like you fix some points, or better said, you remove this, for instance, 2 points from your space, yes? And the homotopy tells you, of this curve, tells you how many times, and in what order, how many times, and in what order this curves wins around these 2 points, yes? And then there is also the homology class of the curve, which is just the same thing as the homotopy, but you forget about the order, yes? So you just say how many times you looped around one point, in this case, or in this case of the torus, one hole, say, and the other. So for instance, these two curves that are, I took the picture from Wikipedia just, but it's like a torus, I hope it's visible, with some curves around them. And these two curves, they cannot be deformed one into the other continuously, staying on the torus, because of course they because they have different homological class. So, okay, and this is an interesting question that I don't know how to approach at all, but there are, of course, like for homotopy and homology, there are also higher dimensional homotopy or homology classes, which is, so for just higher dimensional objects, not curves, but surfaces and so on. So one can ask typical question, what is like, okay, I give you a curve on the manifold. Yes, what is its typical homology class? I don't know. Well, what does it mean? Of course, for probability, it just means that you define a probability measure on the space of curves. Well, better if continuous curves, not absolutely necessary, but certainly simpler. And then you study like, then how many times these random curves, yes, wins around winds around a hole or a point that is missing and so on. It's a random quantity, and you may want to study, you know, the law of this random quantity. It's asymptotic and so on. So this classic has been done for Brownian motion. It's a very well studied subject, and there is an incredible amount of literature. So if you have an integral representation of the invariant, this is very simple. Usually the integral representation, like in this case of the linking number, I put it because one can write it very, very quickly without defining anything. Like, okay, you see, this is a linear expression. So it's a sum, yes, where there is every time gamma 1 dot, gamma s, ds, gamma 2 dot t, dt. Okay, what you have to do if now you have some, I don't know, Brownian motion, or maybe two Brownian motions, yes, linked together. Okay, you just replace gamma 1 dot ds with d gamma 1 and gamma 2 dot dt with d gamma 2. You have to do it carefully because it should still represent the same invariant, because this invariant has a meaning for continuous curves. So it has a meaning also if gamma 1 dot, gamma 2 dot doesn't exist. But so in this case, it's say that the easy guess is to use the geometric rough path. So in some sense, what you will get if you approximate this writing with smooth curves. And but if you write component-wise, you know, the previous cases, this is just Stratonovich. So, okay, so by the end, what I'm trying to say is that there are some interesting integral functions of Brownian motion that you may want to, or Brownian motion or other processes that you may want to understand. And I will just all these will just describe the simplest case, which is real homology. Oops. And I will only describe the simplest the simplest case as well, which is diffusion processes. But there is a recent paper where some natural family of probability measures on curves is introduced, very recent, and it will be interesting to look at the same problem, not for diffusion processes, but for this family of processes, which in the simplest case, like on RD, this would basically just be a Brownian bridge in place of Brownian motion. But for more involved manifolds, it's an interesting family. And since they are closed curves, so they finish where they started, yes, there is some extra interest. So the amount of literature is huge. I finished on this subject by chance, and I didn't expect to be so much studied. So this earlier result is from 58, from Spitzer, it's the same guy of particles, interacting particles, and he studied the asymptotic of winding number of Brownian motion around the origin in R2. So the animation doesn't work on this PDF where I can also annotate, but it's clear, yes, was the winning, like here you fix the origin, you make a curve, and theta t is like the cumulative angle. I mean, if you make one loop, theta counts 1, okay? And doesn't go back to 0, okay? So it's just, okay, you're looking at R2 without the origin. You do not start at the origin because it's not in your space, you start in any other point. And if you look at, I don't know, how many times how many loops around the origin you make up to time t, loops with the sign. So if you go backward or back and so on, you just sum the total angle, yes, every time. And if you divide it by a log t, this converges to a Cauchy random variable when t goes to infinity. The parameter of Cauchy depends, I think, on how far you start from 0 times 0, because I mean, Brownian motion, when there is this call here, you can easily rotate a lot, but then once you start to get lost at infinity, you stop turning a lot. So from time to time, you will come back close to the origin, make a lot of loops, but then spend a lot of time away from the origin. So you see that this diverges very slowly, like log t. but then the limit is Cauchy because when you are around 0, you can turn pretty fast. Of course, it's symmetric, yes. So you could loop in one direction with the same probability as the one you turn in the other direction. So there is a very extensive study series of paper by Pittman York, which is very classical. They studied the very short characterization of the law and the joint distributions with other quantities. And there are contributions from physicists. There are a lot of contributions from conformal field theory. And so there is a very nice paper, for instance, by Jean Bertoine and Wendelin Werner, but I don't know. It's impossible to mention everybody. But there are many results also from the Japanese school. Ito, I think, already started with this business actually. And there is a nice paper by Watanabe. So it's so if you are interested, it's just on the. It's a special issue of a journal, so it's in honor of the birthday of somebody, and so it's very easy to read because it's like it's not ultra technical. It's always explained and so on. And he just makes asymptotic. It's called just asymptotic windings of Brownian motion in Riemann surfaces. So if you want to read something on the subject, maybe it's a good place to start. And so this is the Watanabe of Yamada, Watanabe, and many other results, and many of the students also on the subject. I'm mostly interested to understand what happens on a compact Riemann manifold, and how this. And I just take a diffusion. So this means that a Markov process. This is a Markov process whose generator writes as F is 1/2 the Laplacian of F plus BDF. So here, B is a smooth tangent vector field on the manifold. And this Laplacian is the one associated to the Riemannian metric G. So I will write it slightly later what it means in coordinates, but it's just if you like, if you don't like it and it's like a torus, this just means that this is your Riemannian manifold. Yes, so it's like a square where you identify these opposite sides. This just means the diffusion process with some diffusion coefficient. Okay, and these coefficients tell you the metric, and the drift tells you B up to okay. So and I look at the most classical and well understood objects in this framework that are the empirical measure of this process and the empirical current of the same process. So the empirical measure is just I fix a parameter T positive, which is like the final time, the time horizon in which you look at the problem. So PT of F is just, so PT is just a probability measure. So this is a probability measure. So it's just, when you integrate a function F with respect to this probability measure, it's just 1/T, so it's normalized to be a probability, the probability 0 T of F of XS DS. So PT gives to a subset of the manifold the measure, which is just the percentage of time the process spends in that set. While GT of omega, this is a one current on the manifold, which is, so it gives to a one form omega, just the Stratonovici, the geometric graph path of omega of XS ds. So this is just Stratonovici integral if you want. So you should think of a one form just as a cotangent vector field on the manifold. So that's just a vector. X is also the X is a tangent vector to the manifold. Yes, omega of XS is cotangent, and that's just the product. Okay, so it's just a vector integral if you don't like one form notations. And I studied two problems. One is simple with some hidden problem, which is the large deviation of PTGT. So who is, okay, this large deviation is written in a second, but the main issue will be is the regularity of GT. And then the projection of GT on harmonic one forms. So, you see the space of one forms on the manifold writes as a sum of three. So if you have a one form, this writes as the sum of something exact plus something closed harmonic plus something which is in the co-differential of the two forms. Yes, certainly, this is called Hodge composition. I'm sure you have seen it in one form or another. Like, yes, you can write a vector field on RD as a gradient of something plus something with divergence 0. So that's exactly this decomposition. Yes? So if you think of RD with the flat metric, that's exactly this composition. But so in general, since it's one form, the gradient is really a differential of a function. Then delta eta, so delta is just the dual in L2 of volume, say, of the volume measure on this manifold of the differential D. So this would be something that, like this guy, if you write somehow in coordinates, would have somehow, would be this part with divergence 0, yes, but if the manifold is not simply connected, in general, there are non-trivial harmonic forms, non-zero harmonic forms, which are nicely written in the decomposition. If you want, it's just the kernel of the Laplacian on one forms. So what is here the idea? Yes, if I have this manifold like this, for instance, I can make here some curves, yes, like this one, for instance. It's not important. This is very non-canonical construction. I really specify some curves. This one, then there is these curves. Maybe I can change color just for clarity. Then there is this curve, and this curve. So in dimension 2, if I have 3 G holes, I have 2G such curves. So here I have exactly 6 with 3 holes. And how to say, so now if I have a curve, not necessarily closed, in some sense, I can think that this curve goes a certain amount of times like this curve around the same hole as this curve, blue curve gamma 1, a certain number of times as this curve, black curve here, a certain number of times as this one, and so on. So in some sense, the homology here would just be, if I choose these curves as a base, would just be, so these curves are called gamma 1, gamma 2, gamma 3, gamma 4, gamma 5, gamma 6. So would just be a formal linear combination of these curves, gamma 1, gamma 2, gamma up to gamma 6 with real, I'm considering real homology, with real coefficients. So here it's just R6. So here in this case, it's just R6. And this always, for a complex manifold, is always of this type, R2 something. This something is called the first Betty number, and it's just some space RD, the homology space. But the interpretation is this one. And if I draw some curve, I can, in some sense, associate to it this number, this element R6. And
Mauro, there is a question from DeRham. He's asking if, in the case of two-dimensional sphere, we know explicitly the behavior of pi t and jt. I guess it will depend on the dynamics. But,
two-dimensional sphere,
yes.
Explicitly. So what does it mean explicitly?
I mean, do you know, or you are interested in the large deviation result, but you know to where they converge? I mean, in kind of law of large numbers.
Okay, I will discuss. Yes, convergence is pretty straightforward in the case of compact manifolds.
Okay,
I will discuss it. Yes. But so in particular, I will be interested. Sorry, I didn't see the question. Let me move the. Yeah. Okay. Now I should see something. I'm mostly interested in what JT does on harmonic forms. So in particular, in the case of the sphere, since it's simply connected, there are no such harmonic forms. But still, I will indeed discuss PTJT in general. So
Because in the case of the sphere,
yes,
the decomposition is simpler, right? The hot
yeah, so there is not omega c.
I see. But the boundary term we have also the eta.
Delta eta, yes, if the dimension, except the dimension 1, you.
Okay.
Yes, like not every, if you want, not every tangent field on the sphere will be gradient of a function.
Okay, thank you.
Okay. So, okay, so on that, this is the homology, yes, and okay, homology is if you want, is just the dual of this space, but it has a very nice differential description, which is just you take closed form, so you take one forms such that d omega is 0, okay, the differential of the one form is 0. And you quotientate with respect to exact form. So you say that you identify to one forms if their difference is the differential of a function. And again, these are equivalent classes are called the elements of the DeRham homology. And again, in this case, this is just the dual space of homology. So if the dual of R6 is just R6, okay? So like here, one forms are red, curves are like blue, but the duality is just R6 and R6. So if you want, you can, I don't know, so if I give you a curve and the one form, you can, maybe this I can draw that in black. Yeah, I can integrate the one form of the curve, which just means that I parameterize the curve and I integrate gamma of s, gamma dot s, omega of gamma s is a vector field, cotangent, gamma dot is a tangent vector field, so I can do, so I can make omega of xs act on gamma dot, and then I integrate and in time, and that's, yes, that's the integral of omega of the curve. So, if I have a curve in homology class H and a closed and an omega omega in homology class C, the integral of gamma omega, this is just the duality between this homology and this homology, so HC. Okay? So it's the DeRham theorem, it's Hodge theorem, sorry, the fact that if you have omega, this is decomposed as the sum, and omega c are harmonic. I don't know how to say, you should just define the Laplacian on one forms, and this decomposition is just the fact that this Laplacian is an elliptic operator, so the space of one forms writes as the direct sum of its kernel plus the image of its dual. And then omega c, what is here is just the kernel of the Laplacian on one forms. So it's, is this clear, this picture? Or because I don't know how to say, I'm sure that it's something that everybody studied probably second year, but that's why probably many forgot. It's like, I'm just trying to say that if you have 3 holes, okay, there are 6 one forms on these. So if you have 3 holes, there are 6 possible ways to turn around the holes, and 6 possible ways. So 6 is here. And then if you have a curve, of course, over time, okay, as time goes longer and longer, in some sense, you change in what element in these R6 you are. And I don't know, maybe you turn more and more around this curve, then more and more around this, and so on, for instance. Yes. And if you want to describe how many times, so if you want to describe how many times a curve goes around this hole, you can choose 6, a base of 6 differential one forms that are harmonic. So they are closed and harmonic. So they satisfy both the delta omega is 0 and the omega is 0. And okay, so if you want for each, to describe, so if I have a curve x from 0 to t, I can describe the homology ht of this curve as that unique element in the space of homology, such that when you make it act on a cohomology, so on the quotient of exact form of closed form over exact, it writes as the integral of this special representative of closed form in excess x dot s ds if the curve is smooth. If the curve is not so smooth, you take geometric rough paths. In principle, however, this idea of HT makes sense just for continuous curve, but we don't have just continuous curve. We have a bit of older, thanks to the fact that this excess will be the realization of the diffusion process. So like if you give me a realization of the diffusion process, I can associate to it this homology HT, which, so like if you give me a nice curve, smooth enough curve, I can build this HT. And now if this curve is random, this HT will be random. But it's just a proper mathematical way of telling me how many times you go around this. Maybe, okay, let's take maybe. Why did I take? So if this is not clear, you can just make the same P. It's immediately clear if I make a bidimensional torus. Sorry, I don't know why I made this 3-dimensional with these 3 quarters. So in the dimensional torus, so I can take as a base for the cohomology this one form that is constant going in this direction. This is 1. Okay, it's every point is this direction, and so here it has a 1 hole. Yes, so dimensional torus. So I need 2 one forms in dimension 2, and the other is like this one that goes up. And if I want to know a curve, how many times? Now, if you give me a curve, curves were blue. If you give me a curve, if I want to know how many times it winded up in this direction or how many times it winded up in that direction, I just integrate the one form, I don't know, horizontal, if I want to know the horizontal direction, over, I integrate this blue curve, I integrate the horizontal one form along the curve. And if I want to know how many times it winded along this vertical direction, I integrate the vertical one form along the curve. Okay, so this picture, which is quite obvious on the torus, it writes the same on any Riemannian, compact Riemannian manifold.
I have a question, Mauro. So when you're talking about this homotopy of homology of curve, I guess it's really the homology if the curve is closed, right? But if
so if it's closed, you can make integer homology.
Okay.
So if you want, if it's closed, you can choose. Okay, you can choose these omegas in such a way that this is an integer. Really, for every closed curve, it's just an integer. If it's not closed, it will be a real number. But in any case, as you've seen, I'm interested. So this is not a huge difference. I'm interested when I divide by t. Okay.
Okay. But I was more worried about this invariant via deformation. I guess when you don't have curves which are closed, you don't consider this invariance.
If the curve is not closed, this current that I defined will not be 0 on differential forms, on exact forms. Will not be 0. This will be f of xt minus f of x0. Okay, divided by t. So I can still consider its restriction to harmonic closed forms. Nobody forbids it. But it's true that if for each fixed t, if the curve is not closed, I can define it. I can look at this restriction on harmonic closed forms. But the restriction is not acting exactly on the cohomology, because the quotient with exact form is like is not invariant if I change my one form by an exact form, because in the exact form there is this difference. Right? Okay, yes. So that's, I mean, if you want, take time t and then close it following any geodesic, any path you want after time t. And then this is a closed curve. Once you divide by t, this doesn't change. But this is, in some sense, this is not so nice. The fact that if you want, for each t, the current is not autonomous. It's not zero on exact forms. But in the limit, it will be. Okay. Did I answer your question?
Yes. Thank you.
Yeah, but it's one of the reasons why I told you that you could do the same, say, not on Brownian motion, but on Brownian bridge. And these little things, it goes away. Another thing you can do is that you can, when you consider the norm, you minimize over close. So like the action of JT on exact forms is trivial. It's just the boundary. So divide by t. So you could also just quotientate this away from your definitions. So, okay, the large deviations I really don't want. So it's most of people here know how to make this large deviation better than I do. So the call that we look at these two objects, however, the empirical measure and the empirical current. And this is the generator of the process. And so G here is the Riemann tensor. I will not use this notation, but if you want to write in coordinates, maybe I should have written this earlier. So you just locally on the chart on the manifold, you take the determinant of G equal to 1. This is just take the determinant G equal to 1 is just a conformal transform, which is the functional that appears on, they're not invariant under conformal transform, but they change in a simple way. So you can just take determinant G equal 1 without basically loss of generality. And then, okay, it's just a diffusion, on each chart, it's just a diffusion process, okay, where B is some flat Brownian motion. So first thing we want to establish is large deviations on the space of probability measure times one current. So one currents are the dual of one forms. I'm cheating a bit, and I will tell you just later. So in the sense of, we want to check for the probability that when t is very large, what is the probability? We want to estimate what is the probability that the measure, so the empirical measure of the process is close to a given measure mu. The empirical current of the process is close to a given current J. And we want to check this with speed t. So this goes as e to the minus t I of mu and j. So for those who are asking about the limit when t goes to infinity, this functional doesn't feature any interesting behavior. This functional has only one zero and then is strictly positive. So the only zero of this functional, which I will write in a second, will be the limit but as a consequence, is the only place where its probability is close to 1, and it will be it will be the limit of PTJT in probability in particular. So what does it mean, large deviations? Let me write just like this. So if I take the logarithm on both sides and divide by t, okay. So to be precise, yes, this means that the probability when t goes to infinity, the Lin-Super limit should be the same. And the so once I take just a second. So if I take a look at the probability that PTJT is in the neighborhood of a given point mu j, so this limit, once I make the neighborhood go to mu and j, to just I take this neighborhood smaller and smaller around mu j, this goes as minus I of mu and j, which is, I mean, if you just take the logarithm 1 over t in this writing, and then this being close as the name, being in a neighborhood, that's this informal writing. That's what it means. That's what it means. So
Milton
yes?
is asking if these currents and measures are not free variables, so they are related to each other, right?
they are related in the sense that they issue from the same process. So of course, so if you multiply by t, by the final time, and you may take the derivatives, of course, they satisfy a continuity equation. Already pathwise, because like if you formally derive in time the empirical measure, okay, multiply by t, you just get the boundary value. And if you, so you can write like dt tpt, I think, something like this, formally, plus, okay, let's write it. It's not really, it's the co-differential, yes, of jt. This is 0, yes. Because when you apply this on an exact form, this is just the function. So if you write this on a function f, this is, so yeah, so they satisfy continuity equation, which is slightly, I divide by capital T to normalize. If you don't divide by capital T, they satisfy continuity equation.
This was his question, thanks. Yep.
Okay. But they just do it pi-twice. It's just the fact that when you take Stratonovich or say geometric, if you take Stratonovich integral of an exact form, it's just the boundary, which is the derivative of the empirical method in time. So, it's okay. That's what I mean with large deviations. I'm hiding the compactness issue here, the homology, which is the real question. So I will come to it later. And okay, so sorry. So I just want to tell you who is this functional I of mu and j. So this is the probability that, so forget about closed, for any, like the current acting on all one forms, no restriction. Okay, the probability that the empirical measure closes some mu, the empirical current closes some j goes as e to the minus t I of mu and j. This thing is well defined in the space of lower semi-continuous functional I of mu and j. So I just need to define to you who is I of mu and j. And there are absolutely no surprise, and I think most of the people here there is no like this first result is very absolutely standard. So define the typical current when you are in the measure mu, which is just the integral in the mu of b omega plus 1/2 delta omega. So what is the integral in the mu? So what is here is the thing that if omega is the f, this would be LF, okay? But if omega is not the F, okay, you just add this object. Okay, so this is the typical current while in the measure mu. Okay, I call it. So very simple theorem. If you ever did some large deviation, you just need to build an obvious exponential martingale and do the estimate. So it's very simple. I of mu and j, you have both upper and lower bound, is the supremum over omega of j of omega minus j typical of omega minus 1/2 mu. So mu is here. So the mu which is here in the functional is here, and the j that is here in the functional is here. And this j typical, okay, sorry, mu is also in the j typical, and this j typical is this object. So you see that n plus infinity if j is not holomorphous, if it's not 0 on exact forms. That's exactly what Hubert was saying before, that like, okay, if the curve was closed, already at time t, this would leave, jt would leave on this equal to 0. And now we only have it in the limit. Like if jt of the f is not 0, the price that you have to pay to be close is infinity. Okay? You cannot be close to something which is not holomorphous, to some current which is not 0 on exact forms. Just because when you do jt of the f, this is f of xt minus f of 0 divided by t. So it's not that with big, it's not a question of probability. You just cannot make this thing big. So, and if you want, it's also just exactly. If you check the continuity equation, as Milton was saying, then when you do one thing is divided by t, and the j df is not. So this has to be when on exact terms. Okay, but in reality, what is it? It's very easy to read. Yes, this is in reality 1/2, and this is the L2 norm of. Let me write this: d j minus j mu in the mu. L2 norm in the mu squared. Yeah, because so if J is a J mu typical. Yes, because so what I mean is that J, you should imagine a current as a list of measures, as vector of measures. So if this difference J minus J typical is absolutely continuous with respect to mu, then so it's a vector, but like every component locally, once you choose a chart, if, then this cost is finite. Okay, if it's in L2 is finite, then this is the cost. Otherwise, it's plus infinity. And you also see immediately that I of mu and j, sorry for writing here, but I of mu and j from this, I of mu and j is 0, if and only if, you see, if and only if j is equal to j typical. But look, also jdf should be 0, and j typical mu of df is 0, if and only if mu is the invariant measure, because when I put here omega df equal to df, I get integral in d mu of lf. So if you want that this is 0 for every f, mu must be the invariant measure, which is unique for this process. So I of mu and j is unique if and only if mu is the invariant measure, which I called m previously for the process. And j is the typical current while in the invariant measure. So it's this order, yes. So there is a unique point that this is the limit in probability of PTGT as a consequence of the large deviations. No, like this is for whatever is the Riemannian manifold. There is no, I don't say, there is no transition, there is no non-triviality in this dynamics. So this theorem is very easy to prove. And
I have a small question just to have a better intuition. How do you see from your, I guess, when B is equal to 0,
yes,
then the invariant measure should be the Riemannian, the measure that you get from the Riemannian metric, right? The uniform measure. Mm-hmm. And how do you see this from this expression of I?
Yeah, because this M is the invariant measure for the process. So if the generator is the Laplacian, the only measure that satisfies M of delta F equals 0 for every F is the volume measure.
Okay, thanks.
And then I have another question. So the continuity equation, I should write it in GDF equal to 0. This is the condition that ensures that I, it's infinite if the continuity equation is not satisfied.
Yes, so here there is no, I don't see, the time went to infinity, yes, there is no continuity, there is no time, just I is infinity if J is not aloneness. It doesn't annihilate exact forms. Yeah, because already at time t, Jt of df is f of xt minus f of x0 divided by t. So say that take f any smooth function or continuous function on a compact manifold is bounded. So if your J is away from, this J is not closed, is not alonenous, the probability that Jt is in the neighborhood of this J will be just 0 for t large enough.
Okay.
So, okay, so, but in all this story, I'm just hiding, so getting the functional, and if you want to prove this theorem in a space of distribution for currents, this is very simple, really. You just build the exponential marketing. I don't want, if you ever did bit of large deviations, you know how to do it, or if you do not, it's very simple. So, but what I've been hiding under the carpet is that it is a question of topology. What I didn't, okay, on probability measure taken out of topology, but on currents, what topology am I taking? So large deviation is a topological definition. I'm discussing neighborhoods of J and so on. So what topology on J? And to be completely honest, I didn't even define JT as a current, because I said for each omega, that's what is Jt of omega. There are many ways to see this problem, but say I define, where is it? So let's go back to I messed up a lot with this file. Yes, you see, here if I say PT of F, look, PT of F, there is an obvious pointwise bound. PT of F is less or equal than the C0 norm of F, because it's probability. That I had nothing to. Here, I don't have like an obvious immediate, so I can define this if omega is, say, in L2, just of the volume measure, for instance, yeah? Then I can define GT of omega. It's like from stochastic calculus. But it's not that GT is bounded pointwise by the L2 norm of omega, of course. So what I did is that for every omega, I defined the GT of omega. Is it linear? Yes. GT of omega 1 plus omega 2 is GT of omega 1 plus GT of omega 2. Did I define a dual object on the space of one forms? No, because, okay, there are many ways to see this, but say, a priori for every omega, I have to discard a set of measured 0. There are uncountably many omegas, so I may have to discard a space of probability 1 to define GT. So I've defined on empty, on space of probability 0. Of course, if I know that GT omega acts continuously on some separable space, then I'm done, because I can just define J of omega on a countable dense family, and then I define it everywhere. So this is a well-known problem, which is very, like when you do linear, like there's a difference between defining sort of a stochastic process parameterized by some parameter like omega in a linear way, and defining a dual element of a linear space, random dual element of a linear space. So the rendering is a bit small. So if you want also, you can look at it, you know, leave to rough paths, or consider it or Nostratonovich to martingales, whatever. But at the end of the day, there is a sort of just quantitative object. You want to replace, in some sense, the norm, the probability that the norm is big. You want to estimate that the probability that the norm is big. And what is easy to estimate is the supremum, okay, say of omega bounded in some space, yes, norm of 1 in the space you want to use. And so what is on the left, on the right here, it's easy to do. And this is like having a current. So, so about the existence, yes. So can I define the current? So the current is a random. So JT is a random current in what space? So I don't know what's the first reference by the reliance, but certainly it's in this book already in the 90s, that it is in C minus 1 minus epsilon for every epsilon is strictly positive. And you can also just define it in H minus 1 plus D over 2 plus epsilon. That's a paper 2005 by Flandoli, Gubinelli, and Tortorelli. So this, it's not hard to see these two things. Well, the content of this paper by Flandoli and so on is mostly that if you remove epsilon, you can know. While C minus 1, I think it's not really known, but if H, so how to say, JT doesn't act continuously in some sense on minus 1 minus D over 2. Okay. So you can define supremum over omega such that omega as 1 plus D over 2 plus epsilon of JT of omega, plus epsilon derivative bounded in L2, then it's okay. And here it's not okay. Okay? I mean, beyond the defining, it's something that the estimate you need is quantitative. It's not just about general things. So, so in the Brownian case, but they need D bigger or equal than 3. There is, of course, this question of tightness. I will discuss in a second, and so on, and large deviation in this paper by Kusuoka, Kubada, and Tamura. So this is a PhD thesis of Kubada, who wrote many nice papers on this subject of random currents, Brownian currents, and manifolds. And I'd like to remember him because he passed away very young doing his postdoc in Germany. So this is a bit of the, I don't know specifically this paper, but series of papers this paper is a bit of state of the art of the long Japanese school on this question that comes back to that like is from Ito, students of Ito, and students of Ito. So so they have very unusual techniques for me. So they rely a lot on hit kernel estimates on 1/4, which is nice, and but also they use a lot of the probability of stopping time for Brownian motion, and they need the d is bigger than 3 because it's like, I don't know, some. So the manifold is compact, you have recurrence, but I don't know, if you look at long times, things change. And so what is the non-trivial part in this theorem? The non-trivial part in the general derivation is not to write down the functional, which you can do in a moment, but is to find the right topology, a sharp topology in which it holds. And so you want a topology in which you have a so-called exponential tightness. So the probability that GT is not in a compact set in this topology can be made smaller than e to the minus. So for each L, you find a compact set K such that the probability that you are not in K is less than e to the minus T. That's the idea. So in what topology is this true? So here is our answer, so this topology must be worse than H minus D plus 2 plus epsilon, because otherwise you don't even exist. So certainly you cannot be tight or exponentially tight. So the answer, I'm discussing this not because so I think the answer is more interesting than the question in some sense. So given omega, consider this Hamiltonian, which is just mechanical Hamiltonian on the manifold with potential omega squared. Then there exists a unique constant, C omega, for which you have solutions to the Hamilton-Jacobi-Bellman equation, LG, L, remember, was the generator, plus H of x dg equal to C. So this is like Laplacian of G plus B dg, so maybe 1/2 Laplacian, plus 1/2 dg square, plus 1/2 omega square equal to C. So let's say less or equal to C. This C omega is the infimum of all this constant C. So constant is like a level of energy, for which you can find a G that satisfies the inequality. Then if you take the infimum exactly at this constant, there is a G that satisfies the equality. And all these G are smooth because here you have a Laplacian. I think it's clear. For instance, I don't know, suppose that there is no LG. This C cannot be I cannot solve this equation for any value of C. For instance, the C cannot be negative. Yes, because how can I make it? So there are obvious bounds on who is this C omega. So first, I can integrate this equation with respect to the invariant measure. So you see that the integral of this invariant measure dg is 0, and the integral of h is bigger than the L2 norm of omega, 1/2. So certainly C omega, so whatever constant is here, C omega, I cannot do better than 1/2 omega squared. And on the other hand, taking G constant, for instance, or 0, certainly I can make the inequality if the C is the infinity norm of omega. Because yes, if G is 0, h of x is 1/2 omega square, and G is 0, so 1/2 omega square is everywhere bounded by the infinity norm. Okay, if you just omega, say that omega is smooth. So you can now, with a little work, you can actually bound C omega with the LP norm squared of omega if P is large enough, or if P is just larger than D, not to D, with a function of the L2 norm of the LP norm of omega. And this function is quadratic around 0. Okay, so this is just this constant. This is the critical constant of the Hamilton-Jacobi problem. And then
Mauro, just to let you know, you have more or less 5 minutes left, right?
Oh, goodness. Okay, yes. So, okay, then you can define a sort of Legendre transform, which has also some nice, expression. And okay, you get a compactness if your space has a sort of nonlinear Hilbert-Schmidt embedding into the space with this function phi of omega. if C omega would be the L2 norm, it's worse. C omega is bigger, it's worse than the L2 norm. If it would be the L2 norm, you would get a tightness in the same space where you have existence. You don't, of course, so this tightness is worse. Then using these bounds on C omega, you can try to get a topology on GT, which, if you like Sobolev spaces, which resembles Sobolev spaces. So this you can do and compare in this paper of the Japanese that I mentioned before. So are we sharper or worse than this paper? Well, we are a bit better because we have the equal to. We can manage non-reversible processes or non-Brownian processes. And but on the point of view of integrability, they can deal with better P. So the P on J is the dual of this P. They can make it up to P strictly less than 2. We cannot. But on number of derivatives, we have like slightly better. And we also have some equivalent, not L2 version, but small LP version. Sort of these norms look a bit like LP norm of the Fourier transform if you do it on a topology. So, okay. And then, so let's just go back to the original problem of windings. So I have now this I of mu and J, okay? And I project it, I minimize, so I define a new function, G, on the space of homology, which is just the contraction principle from the deviation from the original J. So I just restrict my J to those that for each omega in homology class C, J of omega is equal to H scalar C. So this is G of, so this H is this H. Okay? So I try to minimize over all the currents that against one forms that encode how many loops you make, give you the number of loops that you decided. So like, I don't know, I want to count what is the probability that up to time t, I make 5t, order 5t. So the number of loops divided by t is close to 5, number of loops around this hole. And this is G of homology of this curve multiplied 5. So so what's called contraction principle in large deviations tells you that the probability that 1 over th is close to h writes as in the sense of large deviations is e to the minus t g of h, and so the main content of what I wanted to do of this work beyond this topology issue, which is quite technical, is to understand something about this functional G. So I just say something about this and I'm done. We distinguish some cases in increasing general. So Brownian case is when the drift is 0. Reversible case is when the drift is a gradient, or better said here, like GB is an exact form. G was the Riemannian tensor. Then I call a quasi-reversible case is GB is closed form. So not exact, but closed. And then there is general case, B is just smooth. And then so here are the results. So the Brownian case, this functional is in bijection with the metric. So this means that if you give me G of H, I can tell you in dimension 2 and only in dimension 2, higher is strictly false. I can tell you who was the Riemannian metric on the manifold. It's like if you observe the Brownian motion for a long time from the realization, of course, you know the metric because like the quadratic variation will basically tell you who's the metric. But you don't need to observe the Brownian motion. You just need for a very long time to know how many loops it made, all the fluctuations of how many loops it makes around the poles of your manifold, and you know the metric in dimension 2. So in the reversible case, of course, G of H is equal to G of minus H and G of 0 is 0 because the process forward and backward have the same law. It doesn't depend on the initial data, this rate has the same law. So, and moreover, you have a quadratic bound with the so-called matrix period. So like homologies is like RD for some D, and you have a sort of canonical scalar product on this RD that depends on the metric. And this rate is bounded by this quadratic form. Sorry, I just have to write here H square. Sorry, there is no image here. So H square is 1/2 m of omega H square. So the L2 norm of over one form associated to this homology. And the equality may hold. And you can make example with constant of some cases with constant curvature when the quasi-reversible case, so the case where GB is closed, not exact but closed, then it's not true that G of H is equal to G of minus H, but you have a Galotti-Cohen symmetry. Namely, G of H minus G of minus H is linear. The difference between looping in one direction and looping in the other direction, the ratio of the probabilities is e to the minus t something which is linear in H. So something which is linear in H means that there is an element in the homology which depends on G and B for which you have this identity. And in the general case, we can say not much. So it's finite and quadratically bounded at infinity. So let me mention just open problems and then done, sorry. So, but I started slightly later. So sharp exponential tightness is interesting, but we are out of energy on this point. I don't know. The sharp exponent as well is a bit of a nightmare. It is limited to extend what I the rates, say, to the case of meromorphic one form. So this means that you don't have a compact manifold, you have a manifold when you remove some points. Like in the case of Pitt-Mayor, yes, you take R2 and you remove the origin. This is different than having a hole. So what is as surprising and very little be studied is that on this kind of structure, there is a natural family of metrics, those with constant curvature, and they are classified by up to isotopic transformation, what's called the Muller space of the manifold. So we would really like all these to say that the final aim in some sense is to study this functional G when the matrix has this property. And so we think that in each of these sort of conformal classes, you can choose a metric that maximizes G. And we would like to understand this G and in this case, the manifold has constant curvature. And the last question is then, can we push? So there is a dynamics on basically complex structures up to some transformation on the manifolds, which is called the Teichmuller dynamics. So you can push this. So since G is clear how it behaves when you make this kind of transforms, you can push this dynamics on G. And can we say something on this dynamics? I have no idea about the answer, and this only works in dimension 2. Okay. Sorry for the very quick open problems list.
Well, thank you very much, Mauro. Yes, so I can either transmit questions from the chat, or you can unmute yourself and ask your questions directly, I think.
So Mauro, yeah, if I give you an atypical behavior, can you describe to me what are the dynamics that the process is following in order to obey to this atypical?
So a typical, so if you give an H, so depends on what you prescribe. If you just prescribe a different current, then yes, this is easy. You just need to you will change B to something. If you fix a different method. So for the general problem, so in the origin, so there are two things. Yes, one is the large deviations of mu J. This here the functional is easy to guess, is an L2 norm of something, and it's easy also to guess the perturbation. So if you give me a mu and a J, it's very easy to guess how you should modify the process. The modified process is still a diffusion process with a different drift. That's all. And this different drift is such that that measure, that current will be the typical one for the modifier. A harder question is, I give you an element of the homology.
Yes.
So how should you modify the homology? So you want to make a lot of loops in this direction. How should you modify the process to do it?
Exactly.
This is not easy because, okay, you can write PDEs, but it's not easy. So the hard part is to decide who is the measure. So no, there is no kind of intuitive, to me, there is no intuitive descriptions of this. But you have, that's exactly the content of this, of in such sense, the result that I made here. So it's not easy to guess how to change it, but you can compare, I don't know, how to change h, how to change to minus h, or you will never do worse than this, or I don't know, if it's quasi-reversible, again, you have this Galotti symmetry. So it's not explicit how to change, but you can compare, I don't know, this kind of things. Like if h is very, very big or very, very small, then you can. So like you can compute, of course, the second derivative around 0, and things like this you can.
Right, thanks for the talk. Very nice.
Okay, thank you very much for the attention. Sorry for the timing. I just didn't realize it.
I'm a bit slow to unmute. I had another question. If you specify a measure which is not the equilibrium measure, and you're trying to find the current for which your large deviation functional is minimal, is it always 0, or do you have, if you want?
No, it's not, no. I mean, if the process is non-reversible, even for the invariant measure, will not be
yes,
0.
yeah, okay.
But say even in the reversible case, no, the current.
So sometimes specifying a measure, an occupation measure which is not invariant, can force a current, even if you're reversible initially.
So no. I think that if the regional process is reversible, you will do it. The optimal current will be no. It's not 0, but it's. I don't know. In the right coordinates, is associated to an exact form. So it's like the right measure times a gradient.
Okay.
So it's not 0, but it's 0 on exact on the f. So J of omega. The optimal J of omega is not 0, but J of the f.
Okay. So it's all it's all about this harmonic part.
Yeah, this part, the rate is not in. The rate is very obvious. There is no. I mean, there is no interesting feature of the rate. Even once you remove points, even for pointed manifolds, there is nothing unusual going on.
Okay.
There are two questions: the topology, which dissolves if you can do something sharp, because there is a long literature on this question, and the second is, of course, the projection, properties of the projection.
Okay, thanks.
May I ask a last question, or?
Yeah, sure.
So it's like a particular case of Claudio's question. It's so if you prescribe some current, may it happen that the way in which you realize this current is not constant in time?
So here time is fixed. Yes, it's going to infinity, and that's so there is no way it can be non-constant in time, because there is no time basically. But if I go back, we didn't study this. I can just tell you what I think. Yeah, we didn't study this. But instead of homology, you can study homotopy. Yes? So in this case, it counts the order. So you should integrate omega that depends on t. Now, I don't know how this should scale with t. This depends on t with big T. But in some sense, so if you want to not to prescribe processes that say it makes 10 loops around here and then 10 loops around here, no matter the order. But you really want to say, first I make 10 loops here, and then I make 10 loops here. Yeah, where you turn first, it's important. Then you should consider forms that depends on time, because like this will tell you when loops happens. So I think that in this case, I understand what you are referring to, like this Bodino and who was simulation and Derrida simulations, yes.
Yeah.
So it's so the answer is that maybe that in reality, if you consider the order also where loops happens, something like this, it's not impossible that appears.
Okay, thank you.
But it will be for homotopy, not for homology. There is no time.
Okay, so I think we can all thank one more Mauro for this nice talk. And I think we meet next week for a talk by Stefano Ola. Yeah, at the same time.
So can you include me in the mailing list?
Yes, I will.
It's quite convenient for me. So sometimes I can participate.
I'll include you.
Okay, thank you.
Okay, bye-bye.
Bye.
Goodbye. Thanks a lot.
Yes.